Friends, again welcome back to our video classes. Last day we discussed the E1 reaction unimolecular elimination unimolecular reactions. Now we discuss about the E2 mechanism, that is elimination bimolecular E2 mechanism. We discuss so we start here. Firstly, for example, E2 mechanism example, this is a compound like this. It's an alkyl halide. Okay, in E2 mechanism, there is a base. It's a single step process. So in the step base comes, that's base. Abstract a proton from the beta carbon. This is the alpha carbon here, and this is a beta carbon here. Abstract a proton from the beta carbon, and so this bond shift like this, and this goes out. And here forms a double bond, C double bond C. And this one will be the product. So, and right of this chemical reaction is equal to, the right constant into the concentration of the substrate, that is substrate into the concentration of the base. Concentration of the base. This will be the right equation, and from here we can clear that it follows a bimolecular mechanism, so or second order kinetics. It follows a second order kinetics. That is why it called as a bimolecular reaction. For example, a compound CH3 CH CH3 Br. This is isopropyl bromide. Isopropyl bromide on reaction with the C2H5 ethoxide ion is an ethoxide ion. Okay, from the beta carbon, this is the beta carbon, or this one is the beta carbon. From these two carbons are similar, one of the hydrogen. This base abstract proton from here, and this bond goes like this, and this goes out and forms CH3 CH double bond CH2 propane, and right of this chemical reaction is equal to K into concentration of this isopropyl bromide CH3 CH CH3 Br into concentration of the ethoxide ion C2H5O minus. Okay, so it depends on the concentration of both the reactants and the reactant and the base. So it follows, the E2 mechanism follows a bimolecular mechanism, or this reaction follows a bimolecular mechanism, that is E2 mechanism. And the base attacks this proton. At the same time, this leaving group leaves in E2 mechanism. So it's a one-step process, a concerted mechanism. It follows a concerted mechanism without the formation of any intermediate. Only transient state is possible here. Next, we will talk about the regiochemistry of E2 reaction. E2 elimination regiochemistry we will discuss. Okay, that means either taram alkenes are formed. That means Shades rule or Hoffman rule that Shades rule more substituted alkenes or less substituted alkenes product by E2 mechanism, by E2 elimination product. That means the regiochemistry. Beta carbon hydrogen abstraction same time alpha carbon leaving group leave this is the mechanism. This leaving group is a better leaving group like halides, chlorides, bromides, iodides and also sulfonates leaving groups. It follows shades of rule. More substituted alkenes product. But in case of fluorides are alkyl halide angle. Then you will get Hoffman product. That means least substitute or less substituted alkenes will be the product. That's how we will see next year. Fluorides, alkyl fluorides, that is fluorides leaving group less substituted Hoffman rule product, alkene product. That's an example. This will be the example. This is a fluoride. Okay, fluoride, you must remember, is not a good leaving group. it is not a good leaving group, so it has not a tendency to leave. Okay, it's not ready to leave. And here the base attacks proton from here, this is a beta position, or from here, these two beta positions, base can abstract a proton from here or proton from here. So we can check the two chances. Okay, base, we can draw the transition states. If base attacks here, the transition state will be like this: fluoride, H, base delta minus. And if the base attacks here, the transition state will be like this: fluoride, H, B, delta negative. Okay, here you can see a charge delta negative. Why this happens? There is a more negative charge here, because this fluoride carbon fluorine bond cannot break when the base attacks here, because it's not a good leaving group. At the same time, this hydrogen carbon breaks, CH bond breaks, and this get a more negative charge or more electron density. Similarly, here this carbon get a more electron density or negative charge. Okay, and this negative charge is stabilized by this fluorine, is a electron withdrawing group. Here you can see fluorine is here and alkyl group here. So this is not much stabilized. It's a carbanion. So this is an electron donating group, and this presence of alkyl group here destabilize the carbanion. But here, this is here the negative charge. Here is the electron withdrawing group present. So electron withdrawing group withdraws the electron and it stabilizes the carbanion here. So this is the stabilized carbanion, and it will give the product. This is the stabilized carbanion transition state. It will give the product like this. Okay, and it also gives the product. If it reacts, it gives the product like this, and this is the major product. It is the major product here, and the least substituted alkane will be the major product, and this is the Hofmann product formed when fluorides, and similarly when leaving groups, the weak leaving groups like quaternary ammonium salt etc. comes, this happens. It follows this Hofmann rule, not the Shades of rule. So when poor leaving groups comes, it follows the Hofmann rules. Like this case, we can see more exceptions to Shades of rule. That means less substituted alkenes will be the major product in cases like that we discussed here, in the case of poor leaving groups. And when the base is bulkier, it also follows the Hofmann rule. That means the less substituted alkene will be the product. And also one more case here, the removal of proton from a more hindered position also favors the Hofmann product, not the Shades of product, that is less substituted products. For example, that means for example this one, okay, 2-bromobutane, when reacted with the C2H5OH O minus, that is ethoxide base, it gives the product like this. This will be the product because it is shades of product, and it according to Shades of rule is more substituted alkane. And the same compound when treatment with tertiary butyl alcohol is the base. If you use the tertiary butyl alcohol as the base, the product will be like this. This is 1-butene and is the Hofmann product. Hofmann rule അനുസരിച്ചുള്ള product ആണ്. This will be the major product in case of tertiary butyl alcohol. So we can conclude that when poor leaving groups present, or the bulkier base present, or the removal of the proton from the more hindered position, it violates the Shades-of rule, and product will be the Hofmann product, that means less substituted alkene will be the product. This is the regiochemistry of E2 reactions. In case of bridged cyclic compounds like this one, okay, so bromine, when elimination takes place, if it is undergo elimination, it will obey the Bridges rule. Only it obeys the Bridges rule, not Hofmann or Shades-of rule. It obeys the Bridges rule. That means the double bond never comes in bridge head position, and the product of this compound will be this one. Okay, never forms a product like this, because here the bridge head is here, so this cannot form. Is the violation of this Bridges rule, and this will be the product in case of cyclic bridged compounds. Okay, next, for an E2 elimination to take place, we know that there is a leaving group and a proton. Okay, so a leaving group here, there forms a double bond. This double bond is formed by the overlap of this carbon hydrogen bond, the sigma orbital of overlap of sigma orbital of CH bond, this CH bond, and the sigma star orbital of this CX bond. Okay, this pi bond in the product is formed from the overlap of sigma orbital of the CH bond and the sigma star orbital of the CX bond. These overlaps and form the pi bond. For this to occur, this should be in the same plane. That means the CH bond and the CX bond, these sigma and sigma star orbitals must be in the same plane for an effective overlap and form the pi bond. Okay, for that there is two condition that the leaving group and the proton should be, maybe they are syn periplanar or anti periplanar. In the first condition, the hydrogen and the X, that means the proton and the leaving group should be syn periplanar. That means for example, hydrogen as a leaving group should be syn periplanar, that means like this, and for Newman projection it is X and this is the hydrogen. Okay, is an eclipsed conformation. The syn periplanar conformation is eclipsed conformation. It is not much stable. Another condition here, in that case H and X are anti-periplanar, where for example H, X, okay, this Newman projection like this, here is the X and here is the H. So this H and X are in opposite, they are anti to each other, and it is a staggered conformation, more stable conformation. And in this conformation, that is when these are in anti-periplanar, there occurs a true and effective overlapping between the orbitals. So for E2 elimination to occur, in most cases the condition will be the eliminating group and the proton, the eliminating groups should be anti-periplanar to each other or trans to each other. 2-bromobutane undergo ozone reaction with sodium ethoxide NOET. It gives the product like this, plus okay, This is the trans product and this is the cis product, and it is almost 81 percentage. It is almost 81 percentage, and also they forms another product like this. Okay, it's almost 19 percentage. This is Hoffman product. Hoffman rule അനുസരിച്ചുള്ള product ആണ്, and these are shades of product, most substituted alkenes ആണ്. Here this is the major product. That means trans product will be the major and this is the minor product. The cis product will be the minor. And why this happens? Trans is more and cis is minor. Why it happens? By drawing the Newman projections, we can we get clear idea about why this happens. The trans or E alkene is major and Z is why it is minor. Okay, for that we are taking the Newman projection. That this is Br, this is H, CH3, CH3, H, H. Okay, this is something less stable product. Sorry, less stable conformer, because here is two bulkier groups in the same side and it gives the product as Z alkene or cis alkene, which is the least stable or minor product. And another conformer is like this, BrH, CH3, CH3, H, H. Here this is a more stable conformer because the bulkier groups are in opposite side, and it gives the product when the HBr eliminates, minus HBr, E2 elimination, the product will be like this. It's a trans product. Okay, this eliminates CH3 and CH3 are in opposite direction, so it's trans or E alkene. E alkene, and it is the major product. Here we can conclude that the shades of products are more predominant, and in that the trans product or E alkene is more than cis alkene. The reason is here one of the possible conformer, another conformer, it is here this CH3 groups are syn coplanar. These CH3 groups are in syn coplanar and less stable. Okay, so it forms Z alkene. It is in minor amount, but this forms a more stable conformer. Here is anti-coplanar CH3 bulkier groups and gives the E alkene, more stable alkene. Okay, in this video we are discussing about the E2 elimination, condition for E2 elimination, the mechanism of E2 elimination reactions. Then after that the regiochemistry of E2 elimination reactions, and lastly the anti-periplanar conformations of the substrate is discussed and how it affects the E2 elimination. In the next video we will going to discuss about more stereochemical aspects of E2 elimination in the next video. Okay, thank you.